So you see that this so you see that this kind of form, so you see that this kind of rule really sort of directly expresses the uniqueness property of this sum type, and really shows us that we're describing the kind of universal property of coproducts here. So if we like, we might like to take this as our sort of assumed inference. So if we like, we might like to take, so if we like, we could take this as our sort of second equational rule for the sum type here. There's a couple of extra little things I should mention about the sum type. Of course, this kind of match function here, it's the kind of thing that, like in this case here, we could sort of write it as u comma v in square brackets. That's the sort of category theoretic arrow which we're trying to sort of model in our type theory. Now, of course, it really depends on u and v. And so if we have, say, u dash, which is equal to u, then we could replace this u with a u dash. And that kind of idea is formalized by this rule here. So this is really saying that if we have our value s of type a plus b, and we have our function u from a to c, and we have our function u dash from a to c, which is equal to u, and we have v equals v dash are our functions from b to c, then this kind of match formed with a u and v is going to be equivalent to this match formed with a u dash and a v dash. Okay, so it's basically just this idea that things formed with equal stuff end up being equal. There's also a kind of alpha conversion principle for this sum type. So basically the idea there is that if we have this term u, which has this sort of bound variable x, well, what if we take that u and we replace all those x's with x dashes, and that'll give us a term which we could call, say, u star. And so then we could replace the x dot u here with an x dash dot u star, and basically all we will have done is sort of taken the bound variable and renamed it x dash. Yes, we'll have a new term, but it'll basically be equivalent, and we could do a similar thing with the v's here. So this is this idea of alpha conversion. Basically, when you have a term with a bound variable, you can rename it as long as it doesn't really affect the sort of true meaning of things. So we saw a notion like that for the lambda type terms, which were the other kind of terms where we had bound variables. And we have a similar thing here when we're forming these kind of matching expressions, because like here we're bounding this x to this u, and similarly here we're bounding this y to this v. So that's basically all there is to these kind of different types and these different rules. So you can check out the document in the description if you want to go into this in more kind of detail. And of course you can get into this very deeply. For example, we went through those proofs of things happening with the Heyting algebra. Of course we can go through similar versions of those things in this more kind of general environment, and we can do things like prove the distributivity law in these kind of bicartesian closed categories. And basically we can show a lot of very useful forms. Now we can't prove all the properties of all the bicartesian properties. Now basically in this simple type theory, it allows us to talk about the kind of general features of bicartesian closed categories. So if we pick a particular bicartesian closed category, like for example set, that might have features which are sort of particular to itself. For example, set has the feature that if we have a couple of arrows, f and g, from a to b, and we have the feature that for any arrow x from the terminal object to a, we have f after x equals g after x, then that implies that f equals g. In other words, if f and g are sort of point-wise equal, in other words, composing them with points always gives the same result, where a point of an object is, in category theory, another phrase to mean where a point of an object in category theory is considered to be an arrow into that object from a terminal object. Well, if f and g compose with points in the same way, then they have to be equal. That's something that happens in set, but that's not something that happens in general bicartesian closed categories. So in set, we can write that if f after x equals g after x for all then so for example in set we have this feature that if we have these arrows f and g from an object A to an object B, they have this feature that f after x equals g after x for every arrow from the for every arrow x from a terminal object into A. Then in the category set, that always implies that f and g are equal, because this is really saying that these are two functions which agree on all elements. However, this statement is not true in a general bicartesian closed category. So this kind of this sort of truth of set theory, or this statement which is true in the category set, is not part of our theory. It's not part of our simple type theory, because our simple type theory is basically the theory of bicartesian closed categories in general, and all the results that we get hold in any bicartesian closed category. So this happens to be a sort of special thing that holds in this category set. So basically what I'm trying to say is that we can model bicartesian closed categories in general, but if there's a special kind of bicartesian closed category, like a hating algebra, or the category set, or the category of categories, or something from logic or whatever that we want to model, we may have to add in some extra kind of axioms, some extra kind of inference rules that we want to suppose are true. And then once we've done that, we can then model these more particular cases as well. But we like to start from this sort of more general case. And another thing we might want to do, for example, is add in ideas like natural number objects, or perhaps ideas like sub-object classifiers if we want to model things like toposes.